Every day, your body pulls in 11,000 liters of air across roughly 20,000 individual breaths. At the exact same time, your heart pumps your entire blood volume through your chest every single minute. To meet the metabolic demands of life, your body constantly solves a difficult physics problem. It must force a slow-moving atmospheric gas, oxygen, into direct, continuous contact with a fast-moving liquid, your blood. The cardiopulmonary unit is an integrated mechanical loop. The heart is the engine, red blood cells are delivery vehicles, and lungs act as a loading dock. Zooming in, deoxygenated vehicles arrive, drop off carbon dioxide, and load fresh oxygen continuously. Human oxygenation requires a highly coordinated electromechanical loop that runs relentlessly from birth to death. The intake cycle begins with an electrical trigger. The phrenic nerve fires a signal from the spinal cord, instantly forcing the diaphragm to contract downward. Expanding the thoracic cavity directly manipulates the internal pressure. According to Boyle's law, as volume increases, the intra-alveolar pressure drops slightly below the atmospheric pressure outside, specifically down to -1 millimeter of mercury. This subtle physical vacuum physically pulls air inside. Once inhaled, oxygen enters the structural manifold. In this hierarchy tree, air travels past the trachea, splitting exponentially through 23 generations of microscopic branches. At the bottom, the massive cross-sectional area takes the rapid bulk flow and slows it down to a crawl. The final destination for this slow-moving air is the alveolar sacs. Here, from 300 million to 600 million individual microscopic pockets sit waiting to receive the oxygen. If you were to flatten out all these microscopic sacs, their combined surface area would cover between 70 to 140 square meters, roughly the floor space of a large two-bedroom apartment. The mechanical architecture of the airway operates as an expansive funnel. It converts the fast velocity of a single breath into enormous surface area, maximizing the physical space available for the air to touch the bloodstream. While the lungs prepare the air, the cardiovascular system manages the liquid. The right ventricle of the heart pumps the body's entire cardiac output directly to the fragile surface of those millions of alveoli. This side-by-side comparison shows systemic circulation on the left pumping at high pressure. On the right, the pulmonary artery operates at a low pressure of 15 millimeters of mercury. If pulmonary pressure spikes into the red, fluid floods the alveolar sacs, halting oxygen transfer. Keeping the pressure low is only half the equation. The system also has perfectly matched ventilation, the air arriving in the lungs, with perfusion, the blood arriving to pick it up. Air is completely wasted if blood isn't routed to the exact same microscopic sacs. To manage this, the body uses a fail-safe called hypoxic pulmonary vasoconstriction. If an area of the lung is poorly ventilated, local blood vessels intelligently constrict. This sudden increase in resistance physically diverts the rushing blood away from the empty zones, cleanly redirecting it toward the fully stocked, oxygen-rich areas. The right side of the heart acts as a low-pressure, auto-regulating pump. It continuously communicates with local lung tissue to ensure blood is only sent to functional, fully stocked loading docks. A red blood cell racing through a narrow pulmonary capillary has extremely limited time, spending roughly 0.75 seconds at the loading dock. In that fraction of a second, complex biochemistry occurs. First, the cell unloads its carbon dioxide into the alveoli. This shifts the blood's local acidity, a reaction known as the Haldane and Bohr effects, which chemically clears the path and increases the cell's affinity for oxygen. The oxygen molecules then passively drift forward, effortlessly diffusing straight across the incredibly thin biological boundary of the respiratory membrane. This biological wall is so incredibly thin, allowing the gas molecules to effortlessly cross from the air directly into the blood plasma. Inside the cell, oxygen targets hemoglobin. In this molecular schematic of cooperative binding, the moment the first oxygen molecule attaches, the protein changes its physical structure. The other three quadrants instantly open up and catch matching shapes, achieving full saturation in just 0.25 seconds. The physical thinness of the barrier, combined with this rapid molecular chemistry, creates what physiologists call a diffusion reserve. Even during heavy exercise when blood flows twice as fast, the engine still has plenty of time to recharge instantly. Because this system relies on such tight physical and chemical tolerances, mechanical breakdowns quickly lead to hypoxia, or oxygen deprivation. These disruptions fall into 4 specific etiologies. Hypoventilation happens when muscular bellows fail to pull in enough air, dropping baseline oxygen supply. Shunting occurs when fluid from conditions like pneumonia completely fills the alveoli, physically blocking the blood from interacting with the air entirely. The remaining 2 failures deal with efficiency. This matrix outlines VQ mismatch, where diseases like COPD destroy airway structures and misalign the timing of the air and blood. Finally, diffusion limitations happen when diseases scar and thicken the respiratory wall, forcing oxygen to travel too far to cross in time. Every single breath requires an immense alignment of physical pressure gradients, fluid dynamics, and molecular biochemistry. Millions of microscopic air sacs must seamlessly integrate with miles of dense capillary networks. Oxygenating the body is the ultimate biological collaboration. The lungs provide massive surface area, the heart provides continuous low-pressure flow, and the blood acts as transport, maintaining a seamless life support system with